All right, the final new reaction we're going to learn this semester is olefin metathesis. And this is a great reaction, led to a Nobel Prize, was really popularized by two chemists, Dick Schrock at MIT and Bob Grubbs at Caltech. Right, so Schrock at MIT and Grubbs at Caltech. And they won the Nobel Prize in Chemistry for this in, I'm pretty sure it was 2005. So very important, very exciting chemistry, and it's going to close up our year with organic chemistry. So let's take a look at the catalyst we use for this, and then we'll look at one reaction, and you have a problem in the daily problems that you use this to come up with a mechanism for a synthesis. All right, and the catalysts for these reactions are very complicated, strange-looking molecules, and it took a very long time for these two chemists to come up with really interesting molecules that did the chemistry they wanted. There are several catalysts that work now. We're going to look at the simplest one, and this is one that Bob Grubbs discovered. Right, so this is known as the Grubbs first generation catalyst. We'll just call it the Grubbs catalyst. So the way it's generally drawn is like that. CY is cyclohexyl. Right, so those are just three cyclohexane rings on phosphorus. So it's tricyclohexyl phosphine instead of triphenylphosphine, which we used for some of our palladium chemistry. And so that's what the catalyst looks like. I don't want to go through it now, but it's a really interesting exercise for you to go through and see if you can convince yourself that that is ruthenium in the +4 oxidation state, so ruthenium 4. Think about the different types of ligands on here and what type they are, whether neutral, negative, positive, that sort of thing. See if you can figure that out. That's what the catalyst looks like. And what these reactions are very good at doing is closing rings. Right? So I have written up there synthesis of cyclic alkenes. And so we use these for ring closing metathesis. All right, and again, this is the Grubbs catalyst. All right, and the types of reactions that we're going to do, I'll just give you an example, and then we'll draw out the mechanism. Is if you take a molecule that looks like that, you react it with the Grubbs catalyst, you can generate that molecule. If you're being diligent in keeping track of carbons, you'll notice something pretty strange about this reaction. So if we number these carbons, you'll note we have 8 carbons in that chain. And if you number the carbons here, actually bear with me, I'll number them a little differently and you'll see why in a minute. You'll note there's only 6 carbons in that ring. And one of the byproducts of this reaction is ethylene, and that's where carbons 1 and 8 end up. Right? So it's a really interesting reaction in that you get a new ring, and you also generate gas, ethylene gas, and that helps drive the reaction. So we actually cleave off the 2 terminal carbons in this reaction, and we'll have to do that in the mechanism. Right? So overall, really interesting synthesis. You'll see here we're forming a cyclohexene. I wanted to just demonstrate this is another way, in addition to the Diels-Alder or an intramolecular aldol, to form a cyclohexene. Olefin metathesis can be used to make other size rings as well. It's very good at medium and large size rings. Not so good at very small rings, but you can make a variety of ring sizes this way. So that's a general example. Next we'll do a mechanism. All right, let's look at the mechanism of this example. And one thing that's important to note is that unlike some of the other catalysts, this actually isn't a catalyst. And actually thinking about it, it is similar to the catalyst you used in the Heck reaction in lab, in that you used something that you put in the reaction that wasn't actually the catalyst, it was a pre-catalyst. Similar in the Grubbs reaction, this is a pre-catalyst. It does one reaction cycle, and then it turns into the actual catalyst for the reaction. Which is this compound, where instead of having the benzene ring, it's just a CH2 group attached to the ruthenium, and that's the actual catalyst. So when most people write out the mechanism of the reaction, they end up just using something that looks like this. So again, Ln, some number of ligands, ruthenium, and then the double bond to the CH2. And so that's what we're going to use as we draw out the mechanism instead of this pre-catalyst, right? So it's useful for us to just write that. That's a pre-catalyst. This is a catalyst. All right. So let's look at what this mechanism looks like. It's a pretty bizarro mechanism, but definitely very interesting. So the key thing to know when you're doing out the mechanism for olefin metathesis, number one, the ruthenium always goes to the more hindered side, which is counterintuitive, but that's just the way the reaction works. It's completely thermodynamic. Putting ruthenium on the more hindered side ends up enabling you to form more stable products at the end. And two, it's all about 2+2 cycloadditions. And we've talked about how those reactions only work photochemically, but when you work with transition metals, the rules for cycloadditions become very different because now you have access to d orbitals. And so it's completely reasonable to do a 2+2 reaction with a transition metal without using light. Right? So what's going to happen is we're going to have the metal approach the alkene like this. We're going to form those two bonds, a carbon-carbon bond and a carbon-ruthenium bond. All right, the mechanism looks just like 2+2 reactions that we've done before. And now we form a four-membered ring with the ruthenium in it. And if we do now a retro 2+2, so this was a 2+2 cycloaddition, now we're going to do a retro 2+2. All right. You'll see that we generate ethylene at this point, right? Our product that we need to form. All right, and now we have generated our compound with ruthenium in it. Okay. So that's our ruthenium intermediate. Let's make sure we don't forget the ligands on ruthenium. And now we can do a reaction with the other alkene, another 2+2 reaction. So we're going to form the bond between those two carbons, right? And again, if we number this out like we did before, we've just cleaved off carbon 1, so that's carbon 1, and now we have 2, 3, 4, 5, 6, 7, and 8. We're going to make the 2,7 bond, right? And we're also going to make, at the same time, clear that out of the way, the bond between ruthenium and carbon 8. All right, so make the 2,7 bond, make the ruthenium to carbon 8 bond, and so this is where we form the 6-membered ring, right? And if we have carbon 2, 3, 4, 5, 6, and 7, we have carbon 8 coming off there, ruthenium there, that's carbon 8. So we've just formed the 6-membered ring, and in the final step, we need to regenerate the catalyst and form the cyclohexene, right? So we can just cleave this, and again, this is our retro 2+2. So that generates our cyclohexene, and it regenerates the catalyst, right? So a really nice example of some different type of transition metal chemistry, very different than the catalytic cycle of palladium, Now again, we're doing 2 plus 2 and retro 2 plus 2 reactions to form rings, right? And you'll have an opportunity to practice this with one of the problems in the daily problems that you'll do for Monday. All right, so enjoy. Olefin Metathesis, great reaction. We'll talk more about it on Monday.